So hello everyone, welcome to the seminar. Today's speaker is Tessler from Weizmann Institute of Science, and his title is already on the screen, so please Ran.
Thank you for this invitation, Lino. So I will talk about open FJRW theory and mirror symmetry. What I'm going to speak about is based mainly on a joint work with Mark Gross and Tyler Kelly, and also a little bit, if we have time in the end, on a work that is now in preparation with Tyler Kelly. Wait, I need to move the Zoom bar. Somehow it's stuck exactly where I don't want it to be. Okay, so I will, okay, so the general content of this talk will be a description of mirror symmetry for Landau-Ginzburg theories whose mirror is also Landau-Ginzburg, which is, well, essentially mirror symmetry for FJRW theories. So the starting point is some sort of duality called the Berglund-Hubsch duality, which is actually a combinatorial mirror symmetry construction for Landau-Ginzburg models. Okay, so in general, when I say Landau-Ginzburg model, I mean that we have a space, some superpotential on it, this W that we have here on board, and a group acting on it, which preserves.
Oh, sorry, maybe it's me, but your screen, at least I see it frozen in the first page.
Say again.
Your screen, I see it kind of frozen on the first page. On the title page.
On the title page.
The screen is showing up as the editor in your laptop or computer.
Okay, that's weird. Okay, so I will try to. Okay, thank you for telling me this. I will try to open the PDF from another place, and give me a second. Okay. So, okay, first of all, do you see what I share now?
Yes.
And now did it move or is it still?
Yeah, it moved.
Okay. Okay, so as I said, Berglund-Hubsch duality is a combinatorial mirror statement between Landau-Ginzburg models. And in general, it predicts a duality, some sort of mirror symmetry, between the FJRW A model, which I will define what it is a bit later, for a given superpotential. In this talk, I will focus only on the Fermat case. So we have a superpotential, which is x1 to the R1, plus x2 to the R2, and so on. And a group, which is ZR1 times ZRn. And such a theory is associated in FJRW model, which I will explain soon. And Berglund-Hubsch duality predicts a mirror symmetry between this model and the Saito-Givental B model, whose superpotential is again the same function, but this time the group is the trivial group. Okay, so what's FJRW theory? FJRW theory is an enumerative theory for curves with some additional spin structures. Okay, later I will actually give very accurate definitions of what it means, but in a nutshell, this is the A model, while the B model is some theory of period integrals with respect to some notion of a primitive form that I will also define soon. So many aspects of this mirror statement have been proven isomorphisms of state spaces, of Frobenius structures, relations between the closed potential. And the topic of today, which is the contribution of my collaborators and I, is an open statement. So what do I mean by that? So Saito-Givental theory gives a Frobenius manifold structure on the universal unfolding of the superpotential, but usually it's complicated to determine its flat coordinates. Okay? Everything will be defined later, but again, I want to give the overview. However, the lesson taken from the case of mirror symmetry for Landau-Ginzburg models, whose mirror is Fano, taught us that somehow the natural way to determine these flat coordinates is by counting holomorphic disks in the target A model, meaning calculating some open Gromov-Witten invariants. So because of it, it is natural to ask whether one can do the same for FJRW theory. And actually, that is what we do. So we will construct fully rigorously open FJRW theories, and we will show that they are a mirror dual to a Saito theory in that sense. Okay, so let's start with a quick review of closed FJRW theory. Okay, I don't know what is the background of the audience, but this is a subject which is already can be considered classical, but let's start with a quick review of it. Okay, so let W be the Fermat polynomial, x1 R1 plus x2 R2 plus xn Rn. The FJRW model involves moduli spaces of W spin curves, which are the following objects. Okay, so first of all, we have stable curves. And in addition, we have spin bundles S1 to Sn. Okay, we have n is the number of monomials in the Fermat polynomial. So we have n spin bundles, whereby spin bundle, I mean a line bundle, or actually an orbifold line bundle, but I will ignore orbifoldness throughout this talk. On the curve, whose R's power is the canonical line, twisted down a few times in each marked point. Okay? The coefficients in which it is twisted down, they are called the twists of the theory. Okay, so again, FJRW theory studies stable curves with an additional structure of more or less R's roots of the tautological line, of the canonical line, and extracts enumerative invariants out of it. So which invariants it extracts? Okay, so let's define the Witten bundle of a W spin curve or W spin moduli space is a derived push forward of the spin lines. Okay, so I have a typo here where I take the direct sum with the fixed S1, but I mean that the direct sum of R pi 1 over the SIs. Okay, so the fiber at a moduli point is just the H1 of SI at this stable curve. The primary FJRW invariants are just the integrals of the Euler class of this Witten bundle, called the Witten class, over the corresponding moduli spaces. Now, why do I refer to them as enumerative invariants? Okay, there are several reasons for it, but one of them is that we can we can regard this Euler class as the weighted signed number of zeros of a generic section of the Euler of the Witten bundle. Okay, and if you think about it a little bit more, you see that essentially it corresponds to counting certain W spin disks. Okay? Okay, so just to get the flavor of how those sections of the Witten bundle look like. So if I take a single spin line, let's say with R equals 3, so it is a third root of the canonical line twisted down once at each marked point, and we have 7 marked points, then we can write this section. Okay? And if you will look at the order of poles then you will see that it is really can be thought of as a section of this Witten bundle. Okay? Now, FJRW theories, they have an associated homological field theory and a Frobenius manifold. Okay, let's start with the original example, Witten's R-spin theory. So now we consider a stable R-spin curve, which is just a stable curve, together with the line bundle whose R's power is the canonical line twisted down AI times in each point Zi, where AI are those twists. It is enough to consider AI in the regime between 0 to R minus 1. And there is some balancing condition that says that if we have a half node, then I will try to annotate. So if we have a half node, do you see what I draw?
Yes.
Yes, okay. So suppose we have a half node. Okay, so I remind you, each marked point is associated with a twist. And if I want this theory to be recursive, then I also want to put twists here and here. Let's call them A. Oh, okay. I don't know why I get these weird dots. And B. So the condition is that A plus B equals R minus 2 mod R. Okay? And at least in genus 0, it fully determines the twist. And all this talk will be about genus 0. Okay, so you can think about it combinatorially, just as a usual theory of marked curves, only that the curves are decorated with numbers between 0 and R minus 1. Okay, so we can consider now the moduli space of R-spin spheres. And okay, it turns out that for some reasons we are not interested in the case where one of the twists is R minus 1. This is in physics literature called the Ramon sector. And we are only interested in the Navier-Schwartz sector, in which all twists are between 0 and R minus 2. And it turns out that there is an arithmetic condition, which comes, of course, from a topological constraint, for when this moduli space will be non-empty. So the moduli space will be non-empty if the sum of twists of the marked points equals R minus 2 mod R. Okay, so for example, let's take R equals 3. And let's choose 4 points. So if I put twists 1, 1, 1, and 1, then the sum is 4, which is 1 modulo 3, which is okay. But if one of the twists will be 2, then I will get sum of twists 5, so there will be no such R-spin curve. Okay? Okay, so let's continue. Okay, so turns out that in genus 0, the Witten bundle that I described before, the derived push forward, is really a vector bundle or an orbital forward bundle, meaning that it doesn't have dimension jump. And we can define the R spin invariance as just the integral of this of the Euler class of the Witten bundle. I should say that this theory, for those of you, I know, heard about Gromov-Witten theory, may say, okay, but maybe it's a little bit esoteric theory. But actually, it has been proven by Pandaripande, Pixton, and Zvonkin that the most general relations satisfied by, tautological relations satisfied by a general cohomological field theory are governed by the three-spin theory. So it carries a lot of information, and actually it is important in many aspects. And Fan, Jarvis, and Wan generalized this theory to more general polynomials. So let me give just one more example of a rank 2 Fermat polynomial, x to the r plus y to the s. So this time I have two spin lines, and they satisfy, oh, sorry, I see that again I have a typo. So SR to the R satisfies, equals WI to minus AIVI, and S to the S, many S's, equals omega twisted down minus BI times VI. So we have now two pairs of, n pairs of twists, one pair for each marked point. And there will be two balancing conditions in each node, meaning that the sum of twists with respect to one, the sum of the first twists will be R minus 2, and of the second twist it will be B minus 2, S minus 2, and so on. Okay. Okay, and we define the Witten bundle as before, and we define invariance and so on. Okay, so now let's move on to what Saito-Givental theory is. Okay, so this time we again consider the same Fermat polynomial, and we would like to define period integrals for it. The way we will do it is that we will consider it a twisted de Rham complex. So instead of considering the usual differential, we will twist the differential by h bar minus 1 dw. Okay, it can be shown that the cohomology is centered in the nth level, where n is the rank of w. And we will be interested in the hypercohomology in this Hn. Okay, so let me give an example for the analog of R spin for x to the R. So now our twisted complex is this one, and we can explicitly calculate everything. So the delta of 1 is R h bar minus 1 x to the R minus 1 dx, and x to the k, its delta is what is written here. And we get a basis for the hypercohomology group, which is just dx, x dx up to x r minus 2 dx. Okay, already it resembles a little bit what we saw in the R spin theory, where the interesting twists were 1 to r minus 2. Okay, but actually the connection will be much stronger than this combinatorial coincidence. Okay, and in general, the hypercohomology will have a basis of pi xi to the ai, where ai is between 0 to ri minus 2 times the form dx1 to dxn. And the proof is a simple computation. Okay, I think that's okay. I will jump over it because we are a little bit slow in time. Okay, so we defined now this hypercohomology, which has representatives as differential forms. So now we can try to talk about integration, because in the end we want to get to period integrals, which are usually the protagonist of the B model. Okay, so in order to integrate, we need to consider some dual homology theory. So in this case, it will be the relative homology of Cn relative to the real part of W over H bar is very small. Okay, and it turns out that there is a perfect pairing between this relative homology and the former hypercohomology, just given by integration, where it is easy to see that it is well defined just by using integration by parts. Okay. Okay, so remember that I mentioned that we have a very nice basis for the hypercohomology, those monomials written here. So we can also talk about their dual basis in the relative homology. So let's denote it by psi b1 to psi bn. And it is dual in the sense that when we pair the monomial of AI with the cycle of BI, we get the product of Kronecker deltas. Okay, so now I want to get to the definition of Saito's primitive form. So as I said before, it is related to a theory of flat deformations of a superpotential. So I would like to start by an example. So let's start with the superpotential W, which is x to the r. And the basic and the simplest deformation we can consider is the Versal deformation written here. We can try to integrate it with respect to a cycle. And actually, this is not that bad. I mean, it might look frightening, but the way to do it is just to Taylor expand around x to the r, and then to do integration by parts using our definition of a dual basis. I will do an example in a minute. So it turns out that certain deformations are better than others. So Saito gave the following definition, that if we have a deformation, Wt, and the power series such that the integral of Wt over H bar times f of omega is to zeroth order just Kronecker's delta. To first order, it is just the deformation parameter Tb to the power H bar minus 1. And then, okay, there are other negative orders. In this case, we will say that f omega is a primitive form, and t are flat coordinates. In a second, we will see that for example, Versal deformation doesn't give a flat deformation in general. Okay, but why do we even care about it? The answer is that we learned from Givental and later FJR and Hellish and Webb and others that when we write things in flat coordinates, the genus zero enumerative geometry of the mirror lies in the H bar minus 2 terms. This is like a Givental's J function for those of you who know. But there is a problem that usually it's very hard to find flat coordinates explicitly. What we are going to show, again, following open mirror statements in other contexts, is that there is actually a very natural way to describe these flat coordinates, which is via certain disk counts, meaning that the coefficients of the deformation of the superpotential will just equal a certain open FJRW disk count. Okay, but of course, in order to do it, we need to define what are FJRW disks, and then we need to find a way to count them. Okay, so let's do this. Are other questions, by the way? Okay. So before I describe, I defined a stable R spin, stable W spin curves, or if you want to think about it in differential geometry, stable W spin surfaces, Riemann surfaces. So now I'm going to add boundaries. So a smooth marked disk is just a disk together with distinct internal marked points, which I label Z1 to ZL, and distinct boundary marked points, which I label X1 to XK. And a stable marked disk is just a collection of smooth marked disks and spheres connected by simple nodes, such that the topology obtained after I smooth it is that of a disk. Let me draw something like this. Okay, so here I have three disk components, and from the leftmost one, we have a sphere bubbling. The leftmost disk has two boundary marked points and one, a boundary node and an internal node. The middle disk has two boundary nodes, one boundary marked point and one internal marked point, and the rightmost disk has only one boundary node and two boundary marked points. So this is an example of a stable marked disk.
Are the boundary marked points cyclically ordered, or you don't care about that?
Yes, they are cyclically ordered. So people study in other contexts, also cases in which you don't limit the cyclic order. Usually, okay, it is important mainly for real Gromov-Witten theory. But somehow, real Gromov-Witten theory, its information is contained in that of open Gromov-Witten theory, because, I mean, you can always split the moduli into pieces with given cyclic orders. But yes, for the sake of mirror symmetry and for open Gromov-Witten theory, then I want them to be cyclically ordered.
Okay, thanks.
Now, because I know that most people are more used to the closed theory, so let me tell you that there is a very natural and useful map that allows us to take an open object and embed it in the closed moduli space, and this is the doubling map. So the doubling map you are given a stable, let's say, disk, and you take another copy of it, but with an opposite complex structure. You glue them together along the common boundary, and what you get is a stable sphere. Okay? And many times it helps us, because we feel better with spheres, it helps us imagining a few things. So for example, we learned that in open Gromov-Witten theory, we have three types of nodes. You see them in the pictures. The leftmost one. In these pictures, the gray part, the darker gray is the original disk, and the bottom part is the conjugate part. So we see that in the left picture, we have an internal node, and also there is a conjugate internal node. In the middle picture, we have a boundary node. The third picture describes the situation in which the boundary itself contracts into a point. So that's a contracted boundary node. Okay? Okay, so we defined now stable disks. We can now define what are stable R-spin disks. And one way to do it is directly in using the disks, but because I already defined the doubling map, I will do it actually using the doubled surface. Okay, so a smooth W spin disk for W like a Fermat polynomial is a stable marked disk, like before, together with RJ spin bundles over the doubled surface. So, okay, we defined in the closed setting what are RJ spin bundles, and the double surface is a closed surface, so I just use this definition, only that I require that the twists at conjugate marked points will be the same, okay? And moreover, I want the involution, so I should have said it before, on a double surface, we always have an involution, which takes the darker gray to the less dark gray. Okay, so we want that our spin lines will have also an involution which will be compatible with the natural involution on the cotangent line on omega. Okay? And again, there is a arithmetic constraints that we need to have in order for this structure to exist, which is exactly the constraint actually I wrote before, only that I use the fact that now for each internal marking, I need to count it twice, once for it and one for its conjugate. And now there is something which is, on the one hand, very important, but on the other hand, I think that in a first talk on the subject, I will just mention that it exists, but I will not get into it. So, I mean, essentially, we consider spin lines on a disk. And because the disk has a boundary, it is natural to ask also for the spin lines to have some sort of boundary condition, which will be some sort of a choice of an involution invariant ray. Okay, this is what I call grading, but I will not expand on it. It is very important, and it adds another arithmetic condition for each line bundle, this time a mod 2 condition, not a mod RJ condition, but I will not talk about it here. Anyway, we can now define the open Witten bundle. So the involutions, they lift also to the Witten bundle, and we can just take its involution fixed part as the open Witten bundle. Okay, so in the closed setting, we counted R spin spheres just by looking at number of zeros of a transverse section of the Witten bundle. And why did this definition make sense? Because first of all, both the complex Witten bundle and the complex moduli have canonical orientations, I mean complex orientations, and the moduli itself was compact and boundaryless. However, in the open setting, this is not the case. For example, the moduli of a disk with three boundary markings and one internal marking, okay, and okay, they're labeled, so looks like a hexagon where these faces correspond to disks, stable disks of this form, of this form, and the other boundaries correspond to stable disks of this form. Okay, and the corners corners look like this. So we see that our moduli space has a boundary. Not only this, it is not canonically oriented. Actually, in higher genus, it may not even be orientable at all. Okay, so already these are serious obstructions for integration. Okay, but fortunately, we can solve the orientability problem. And it was proven by Sasha Burek, Emily Klader, and myself in the case of R-spin, and by Mark Gross, Tyler Ken, and myself for general FJRWs, for more general FJRWs, that while the moduli space is really not canonically oriented, it turns out that also the Witten bundle is not canonically oriented. However, the total space is canonically oriented. So in other words, they're relatively canonically oriented, which is good enough for integration. I mean, at least it solved the orientability problem for integration. Again, there is, of course, the more crucial problem is that of existence of boundaries. So the way to overcome it is to put boundary conditions. But, of course, even in the hexagon example before, there are infinitely many ways to put boundary conditions, and different choices will give us different zero counts for sections. So the question is there a natural way to put boundary conditions? So what we would like our boundary conditions to be, we would like them to be geometrically meaningful. And okay, and we also hope that the resulting theory will be related to those flat coordinates that was, as I said, an original motivation. And it turns out that we can achieve both of these, and actually in a very canonical way. Let's start with describing the rank 1 case, the R-spin. Okay, let's go back to the B model. I promised before that I will show you why versal deformation is not flat, is not good enough. So let's try to integrate with respect to the versal deformation. And what we get by doing integration by parts and using the definition of dual basis and so on, that the first order is indeed 1, which is good, but then the zeroth order is 1, the -1 order, which if it were flat, it should have been S0. That was our original definition of flatness. In this case, it is not S0, but it is S0 minus 1/8 S2 squared, which is bad. It means that our coordinates are not flat. Okay, I mean, if we do the all three integrals, we see that the only problem at the moment is for the zeroth integral. Okay, but we can actually try to fix it. So we can take T0 to be S0 minus 1/8 S2 squared, T1 to be S1, and T2 to be S2. And now we got something which is really flat. Okay, so these T's, in this case, are flat coordinates, and dx will be a primitive form. Okay, if we try to play this game for the more complicated 10-spin theory, we will get a much more complicated expression, which, okay, we can still try to calculate it term by term, but it turns out that in a special case of R-spin, there is actually a closed formula. Okay, so this closed formula was discovered by different authors in different scenarios, let's say. but essentially they are all equivalent. And it says that we can write the flat deformation of x to the r using those coefficients written here, those bracket coefficients. Just as a spoiler, this 1 over r corresponds to them being r spin invariance, and the O corresponds to them being open R spin invariance. But it turns out that with this choice gives the closed formula for the flat coordinates. And in a sense, if you put some grading condition, some homogeneity condition, it is the only flat coordinates. Okay, so mirror symmetry insight will tell us, I mean, that's the philosophy that I repeat throughout this talk, that we would expect these brackets to be open R-spin correlators. Okay, so there is at least one good thing. At least they look like correlators, because no one uses those brackets for things which are not correlators. So at least notational-wise, we are okay. Okay, let's now talk about the A model and see, I mean, can we make it work? Okay, so I remind you, we want to define an open R-spin theory, meaning actually to put boundary condition for sections of the Witten bundle over the moduli that will yield the numbers that we get from the flatness equations. Okay, so when we look at the combinatorics of the non-vanishing coefficients, I mean, by combinatorics, I mean, when we look for relations between R that we see here, K that we see here, and those twists that we see here, so it turns out that they are not arbitrary. And they put some grading for the boundary states, which when we try to analyze it, we see that all boundary twists must be R minus 2. Okay. Now, the second hint we get is that there is no non-vanishing for odd-dimensional moduli spaces. I mean, if I consider the Witten bundle over an odd-dimensional moduli space, I don't get 0. Now, it looks something very modest, but there is a very simple involution that you can always do whenever you have a vector bundle, a real vector bundle over a real manifold of odd dimension, which shows you that its Euler class must be 0. And this involution is just replacing a section S that you use in order to calculate the Euler number with minus S. It will have the same zeros, but the signs will be opposite. But here we see that we cannot, for some reason, we don't get zeros for odd-dimensional moduli spaces, meaning that this involution doesn't respect our boundary conditions, which means that there is some sort of symmetry breaking between positive and negative. This is related to this thing that I mentioned before, but didn't want to expand on, this grading. But let me say that there is a certain hidden positivity in the open theory, positivity which is completely lacking in the complex theory. In Witten's original R-spin theory, there is no notion of positivity, but in the open theory, it is there and it is super crucial. And you can learn it just from looking at the combinatorics of which numbers vanish and which not. Finally, there is a recursive structure of equations and moduli spaces, which tells us that somehow our boundary conditions should be well behaved with respect to the compositions that, you know, associahedra like the compositions of moduli spaces and forgetful maps. So with Sasha Buriak, Emily Kleider, and myself, and later with Mark Ross and Tyler Kelly, we showed that there exists a definition of R-spin discounts which satisfy the flatness equation, and in particular, they give us the coefficients of the flat deformation. And actually, there is another very nice property of them, is that the genus zero potential is the genus zero part of the Gelfand-Dickey wave function. As a general knowledge, I will say that in Witten's original R-spin theory, closed complex R-spin theory, the potential gave the Gelfand-Dickey tau function. And it is something that we observed in the study of this theory and an earlier theory, that in many cases, when the closed theory is governed by a tau function of an integrable hierarchy, the open theory, if you can construct it rigorously, will be governed by the wave function of the same hierarchy. Okay, so here I give examples of sections, but forgive me, I will skip them again. I mean, the only reason I planted this slide is that you will see that on the one hand, you can really write sections of the Witten bundle. It is really something that you can feel. It is not something too abstract. But on the other hand, they're not simple, as you can see. Anyway, let's move on to rank 2, where there is even more action. Let's try to do the deformation for rank 2. So, again, we start with the Versal deformation. And let's, again, restrict to R equal S equal 4. It's a compact enough example. But actually, let's even compactify it more by setting all coefficients of the Versal deformation, but the one of x squared, y squared to 0. Okay? Let's try to see if this guy gives us a flat deformation. So again, it's very easy to see that it doesn't. However, here we already see a new phenomenon. Okay, so when we try to integrate, we get not only a single or a finite number of bad terms, we actually get an infinite number of bad terms. And we want to kill all of them and to leave only the P22 term. Okay? So we have infinitely many constants to fix. But now comes a very interesting point. Unlike the R-spin case, there are two ways we can fix, let's say, the first term, the T22 squared term. One way is to add T22 squared x to the 4 to the superpotential. And the other is to add T22 to the squared y to the 4 in order to cancel this guy. And actually, it's even worse. Any linear combination of them, such that the coefficients will sum to 1 over 8, will make this correction. So it looks like that now there is no unique solution of the flat family. Interestingly, the FJRW invariants that I'm going to quickly describe will exactly fill this non-uniqueness. Okay, so again, consider this W. And again, we can learn some hints from just from the flatness equations. So again, from combinatorics of the non-vanishing numbers, we see that the all boundary points must have twists which are r minus 2, 0. Again, I remind you that now twists are a pair because we have two bundles. So there are either r minus 2, 0, 0 s minus 2, or r minus 2 s minus 2, where the latter can appear only once. We also have indications that the Witten bundle that also boundary conditions should be direct sum. But we see that if we pull back the boundary conditions from R spin and F spin from the two spin bundles, they are not enough. They don't specify boundary conditions for all the boundaries. Okay? So unlike the R spin case, they will not give us well-defined numbers. However, these non-well-defined numbers will not be completely non-well-defined because it will turn out that some combinations of them will be well-defined. Okay, so let me give an example. So I remind you that before we saw that the flatness equation for the B model doesn't specify exactly what are the flat coordinates, and we saw that the coefficients of t2 squared x to the 4 and t2 squared y to the 4 are not fixed, but only that their sum is fixed. Now, according to our philosophy, one of them, this guy, should correspond to intersection number over this moduli. I mean, it counts disks which have 4 boundary marked points of type X, of type R minus 2, 0, while this should correspond to this moduli space. It counts disks which have 4 boundary marked points of type Y, of type 0, S minus 2. Now, interestingly, it turns out that among all possible boundaries of the moduli space of interest, the only boundary conditions which are not determined are boundary conditions for strata of this form. So strata of the following form. So we have here, this will correspond to the moduli of disks of the form. So here I have R minus, sorry, R minus 2, S minus 2. Yeah, I don't know why I have these annoying dots. And an internal marking. Sorry, and 2 internal markings. And here I have just 4 points of twist R minus. Okay, so yeah, actually in our case, R and S are just 2, so I can actually just write it as 2 and 2, and here I have 4 points of twist 2 and 0. While here, here, what I have is a very similar moduli, only that here the points will have twists here they will have twists 0, 2. Okay, so the moduli spaces, they have many boundaries. For most boundaries, I get boundary conditions by the previous considerations, but there are exactly one boundary for this moduli space and one boundary for this, for which I don't have well-defined boundary conditions. And it turns out that even though I don't have boundary conditions which are strong enough to specify the zero count for each of these moduli spaces, it turns out that just by my requirement that the boundary conditions will be well behaved with respect to the compositions of the moduli space, they impose that even though I don't have a well-defined zero count here and a well-defined zero count here, the sum of zero counts between the two is well-defined. And actually, turns out to be exactly 1/8. By the way, if you're interested how can I have fractions, it is an orbifold theory, so I can have fractions. So we see that the exact degree of freedom we had in the choice of flat coordinates, we also see it in the geometry of the A model. Okay, so the theorem of Mark, Tyler, and myself was that there exists a definition of open rank 2 Fermat discount, and that the discounts satisfy the flatnet equations, and they are uniquely determined up to the same wall crossing group as in the B model. Moreover, every rational solution of the flatness equations in the B model can be realized by this construction. And the reason for the wall crossing that we see already in the algebraic theory of Saito is exactly that there are certain boundaries that are really untreated. There is no natural way to treat them. Okay, so this provides a complete and intrinsic open mirror theorem for this case. And now Tyler and I, we write the more general case. So in the more general case, there are a few extra complications, which are again solved by mirror symmetry intuition. But the upshot is that there exists a definition of open Fermat discounts for all possible Fermats, and actually it extends, the theorem essentially holds for all concave open Gromov-Witten open FJRW theories, for those of you who know what it means. I mean, these are the theories that you can define without the need to use virtual techniques. And the resulting numbers satisfy the flatness equations, and again are subject to the same wall crossing group as the B model. Okay, so I think I will stop here. So other questions?
Thank you very much. So, questions? Okay, so maybe I'll ask a couple of questions. So in the end, do these boundary conditions, can you describe them just from the point of view of the moduli spaces, or?
Yeah. I mean, okay. I gave above an example in the case of R spin of a very explicit section. But this is not the good way to describe them. The good way to describe them is as follows. When you look at boundaries of the moduli space, let's say in codimension 1, then you get a decomposition into more or less product of two moduli spaces, the one on the left and the one on the right. Okay, I mean, you have something like this, which has its combinatorics. Something like this, which has its combinatorics. And I remind you that the combinatorics is not only how many points you have, but also what are the twists. Okay. Let's talk about R spin just because it will be easier for me to say what I want. So in R spin, I remind you that I said before that, okay, so we have these two twists. Let's call them A and B. And A plus B equals R minus 2. Okay, I said R minus 2 mod R, but the only case that the mod is important is the Ramond case, which doesn't contribute for other reasons, so let's ignore it. A plus B equals R minus 2. If A and B are greater than 0, my boundary condition will be to require that when I evaluate the section of the Witten bundle at the node. Okay, so there is an evaluation map. I didn't talk about it because I didn't get too much into details, but there is an evaluation map. When I evaluate the section of the Witten bundle at the node, I want to get something positive. So you can ask, wait, how can I say that an evaluation of a line bundle is positive? The answer is, this is where this thing that I mentioned before, the grading enters. The grading gives you a notion of positivity for the spin line and hence for evaluations of the Witten bundle. So if A and B are both positive, I want the evaluation to be positive. On the other hand, if A or B is 0, then you can see geometrically that after you normalize the stable disk, you cut along the node, you can forget the side which carries the twist 0. Just forget it. The usual forgetful map you have in modular spaces. If you require now that boundary conditions in such boundaries will be pulled back from the moduli obtained by the forgetful map, I mean, that essentially they don't see the half node with twist is 0. If you make this requirement, then the combination of this requirement and the positivity requirement specifies all possible boundaries for R spin. And it turns out that with these boundary conditions, you get the Gelfandiki hierarchy, you get the mirror symmetry, and so on. Now, you can ask, okay, why can't you do it, for example, for rank 2? So in rank 2, you can do it for almost all boundaries. So now I have something like, so here I have A and A prime. And here I have B and B prime. It's something that my editor started to do yesterday, these annoying dots. So I'm sorry that they appear everywhere, but I don't know what to do with them. So I have A and A prime and B prime. If you just pull back the R spin boundary conditions I described on the left, it will fix almost all boundaries. Which boundaries it won't fix? Boundaries of the form R minus 2, 0, or boundaries of the form 0, S minus 2. In the for example I showed before, these were exactly those 2, 0 and 0, 2. These boundaries, for them, you don't have, R spin doesn't tell you what to do. So you can say, okay, maybe we should do something smarter than R spin. But actually also mirror symmetry doesn't want you to do there anything. So you just don't do anything there, okay, except of course requiring that, the Witten bundle decomposes over the two pieces of the moduli, so you want also the section to decompose. But if you just say this, it will just give you exactly what you want. However, in higher rank, when there are 3 or more copies of the Witten bundle, you need to work harder. There you really need to impose new boundary conditions. But you can do it in a very natural and canonical way. And it gives you a perfect mirror theorem between the A and B models. By the way, I should say, even showing for R spin that you can really find a section which satisfies this forgetful map and this positivity is not a trivial task in real algebraic geometry, because these positivities are somewhat contradicting each other. But it turns out that it's really a miracle that you can do them. And it's very nice that this real algebraic geometry miracle allows you to construct an enumerative theory that you can calculate, and moreover gives you the mirror dual to the Saito theory.
And am I correct that if you take R in the R spin case again, if you take R equals 2, do you get something like the theory of a point, or?
Yes. So R equal 2 is something that with other collaborators in genus 0 it was with Jake Solomon and Raul Pandaripande, in higher genus with Jake, and then the study of its relation to KDV was with Sasha Buryak. So there we were able actually to push those statements to all genus, because this is the only case where you can actually study all genus without virtual techniques. I mean, virtual techniques, while they are super standard in closed Gromov-Witten theory, they are much less standard in the open. I mean, there were a few breakthroughs in the last few years, but these breakthroughs are still not enough in order to define, for example, open R spin in higher genus. I should say that it was a very, I mean, we worked really hard, and in a week or two, with Ethan Zhao, we are going to publish a construction of open R spin for genus 1. We were somehow able to solve the virtual problem there, and what is nice is that you get the genus 1 part of the Gelfand-Dickey wave function. Anyway, yes, the R equal 2 theory is the theory of a point. From the mirror symmetry point of view, it might be a bit dull, but from the integrable hierarchies point of view, it's very interesting and rich.
Okay, thank you. Any other questions? Last opportunity. No. Okay, so that's it for today's seminar. Thanks a lot, Ron, for a very, very interesting talk.
Thank you for the
And that's it for
invitation.
today.